The number on NOAA's Space Weather Prediction Center forecast this morning is 3, KP3. That is the index value describing Earth's magnetic field activity right now, the scale that goes from 0, completely quiet, to 9. The G5 extreme storm level that in May 2024 produced the most intense geomagnetic storm since 2003, sent the aurora visible over Mexico and Florida, and had power grid operators from Canada to the UK running emergency protocols. KP9. KP3 is quiet. No G1 or greater geomagnetic storms are expected for July 26th through July 28th. No significant transient or recurrent solar wind features are forecast. The 3 CME sequence that delivered glancing blows to Earth's magnetosphere on July 24th and 25th, none. The pair of CMEs from July 20th and 21st, combined with the coronal hole high-speed stream that this channel covered in detail, has passed through. The magnetosphere is recovering. The aurora that lit up skies across Canada and the northern United States during the July 3rd through 6th machine gun sun sequence, and again briefly during the late July CME arrivals, has faded back to polar latitudes where it belongs in a quiet period. To most people looking at these numbers, the solar story of July 2026 looks like it is winding. Now a rest. Normal summer quiet, settling back in. The space weather scientists watching the solar disk right now are not looking at a rest. They are looking at a pause. And they are using that pause to track several specific things on the sun's surface and in the data. From the DS-COVAR and ACE satellites at the L1 Lagrange point that will determine, not might determine, will determine, whether August 2026 becomes a repeat of July's machine gun sun, or whether the solar cycle's maximum phase is beginning its transition toward the declining plateau that will eventually lead to solar minimum in the late 2020s. This is the week that sets that trajectory. And to understand why, you need to understand the most fundamental repeating pattern in solar physics, one that has been operating for 4.5 billion years and that drives every forecast, every watch, every warning that NOAA's Space Weather Prediction Center issues. The sun rotates, not all at once. It is a fluid body, and like all fluid rotating bodies, its equatorial regions rotate faster than its polar regions. The equator completes one rotation in approximately 25 days. The mid-latitudes take about 27 days. The poles take roughly 35 days. The 27-day figure is the one that space weather forecasters use as their baseline, because most of the active regions that produce major solar flares and Earth-directed CMEs form in the mid-latitude belt between roughly 10 and 35 degrees north and south of the solar equator, the same latitudinal band where sunspot activity concentrates during solar maximum. What this 27-day rotation means in practice is that any active region on the sun's surface that is visible from Earth today will rotate out of view in approximately 2 weeks, disappear around the sun's western limb, spend roughly 2 weeks on the far side, invisible to Earth-based or L1-based monitoring, and then return around the eastern limb to the Earth-facing disk approximately 27 days after it was last visible. If that active region has maintained its magnetic complexity during its 2 weeks on the far side, which complex, large, active regions frequently do, it arrives back at the Earth-facing disk carrying the same flare potential it had when it rotated out of view. Active region 4479 produced an X1.1 solar flare and full halo coronal mass ejection on June 30th, 2026, prompting SWPC to issue a G2 moderate geomagnetic storm watch for July the 3rd. 9 separate flare events at M1.0 or stronger occurred in the 7 days surrounding that period, including multiple M-class flares on July 1st. Solar activity was elevated during that period with 9 events at M1.0 or stronger, including the X1.1 at 2050 UTC on June 30th. Active region 4479, the region that launched the X1.1 full halo CME at 1,496 km per second on June 30th. The region that Dr. Timothy Skov called the machine gun sun, when it continued firing in rapid succession through the first week of July. The region whose activity this channel tracked through the G2 Stormwatch, the aurora visible across the northern United States, the 10 flares in a single 24-hour period that defined early July 2026 as one of the most intense brief solar activity periods in recent memory. Active region 4479 rotated onto the far side of the sun in the second week of July. It is currently invisible to every instrument at L1, to SOHO, to stereo, to every satellite watching the sun's Earth-facing hemisphere. And based on the 27-day rotation arithmetic, starting from its most active period in late June and early July, it is due to return to the Earth-facing disk somewhere in the window between late July and early August 2026. This week. The next 7 days. When it returns, 2 scenarios are possible. In the first scenario, active region of 4479 has decayed during its transit across the far side. Its magnetic field has simplified, its sunspot group has reduced in size and complexity, and when it appears around the eastern solar limb, it presents as a moderate or weak active region with limited flare potential. This scenario would be consistent with the natural aging process that most active regions go through over a full solar rotation. It would suggest that the intense activity of late June and early July represented a peak of activity for that particular region, and that the solar cycle's maximum is still active but not intensifying further from that specific source. In the second scenario, active region 4479 has maintained or reorganized its complexity during its far-side transit. Large, complex sunspot groups can sustain their magnetic configuration across multiple rotations. The history of solar cycle 23 and 24 include active regions that produced major flares on multiple successive rotations of the same region. When AR 4479 rotated away from Earth, its classification, the measure of magnetic complexity that NOAA uses to rate flare potential, was at the highest levels observed for any active region in 2026 to that point. If that complexity persists, its return to the Earth-facing disk could initiate a second machine gun sun sequence, potentially more intense than the first, arriving at a sun that has already accumulated additional magnetic energy in the weeks since the first sequence. Space weather forecasters cannot currently observe active region 4479 directly. This is the fundamental limitation of solar monitoring from Earth's perspective. The far side of the sun is a blind spot. The stereo spacecraft that historically provided far-side coverage operated in heliocentrically opposed orbits that allowed observation of the hemisphere facing away from Earth. But the current status of the stereo mission means that complete far-side coverage is limited. Scientists can infer what is happening on the sun's far side through a technique called helioseismology, using seismic waves in-sea to the sun to image magnetic structures on the far side, the way seismologists use seismic waves inside the Earth to image its interior. But this provides lower resolution than direct observation. The first clear view of what AR 4479 looks like after its rotation will come when it appears around the eastern limb. And when it appears, NOAA will have approximately 24 to 48 hours to assess its magnetic configuration before it reaches the position on the solar disk from which Earth-directed CMEs are most efficiently launched. This is why this week decides everything. No T, because a major solar storm is certain. Because the first view of AR 4479's post-rotation state, when it comes, will immediately tell scientists whether August continues July's machine gun sun pattern or whether the solar maximum is beginning its natural wind down toward the moderate and then declining activity levels that precede solar minimum. But AR 4479 is not the only thing on the solar disk today that scientists are monitoring, because EarthSky's July 26th solar update, covering the current state of the sun with fresh imagery from NASA's Solar Dynamics Observatory, flags something in its top story that deserves specific attention. Today's top story: big filament eruptions. The GOES-19 SUVI instrument captured the scene in its 304 angstrom wavelength channel. Large filament eruptions on a nominally quiet sun, at the moment when most people have moved their attention away from solar activity because the CME sequence of late July appears to have concluded. A solar filament is a long, dark structure visible in hydrogen alpha wavelength imagery of the sun's chromosphere, a dense, cool concentration of plasma suspended in the solar corona by magnetic field lines. Filaments can extend hundreds of thousands of miles across the solar disk. They are often associated with what astronomers call prominences when viewed at the limb of the sun, the same structures, seen from the side, that arc above the solar surface in spectacular looping formations visible during solar eclipses. When a filament erupts, when the magnetic configuration suspending it becomes unstable, it can launch a coronal mass ejection into the solar system. The critical distinction between a filament eruption and a flare associated CME is visibility. CMEs associated with solar flares are typically bright, fast, and easily detected by coronagraph instruments like those on SOHO and NASA's GOES-19 CCOR-1 imager. CME clouds from filament eruptions are frequently slower, fainter, and harder to detect in coronagraph imagery, particularly if the filament is located on a part of the solar disk where the resulting CME is not obvious against the background corona. These are called stealth CMEs, coronal mass ejections that depart the sun without producing the obvious visual signature that allows forecasters to immediately characterize their size, speed, and direction. Stealth CMEs are not slower because they are weaker. They can carry significant magnetic flux and produce substantial geomagnetic storms on arrival. They are simply harder to see until they are already en route. The DSCOVR satellite at L1 provides the definitive real-time measurement of any arriving solar wind structure, but DSCOVR sits approximately 1.5 million kilometers from Earth, roughly 1% of the Earth-Sun distance. The warning time between when DSCOVR detects an arriving CME and when it reaches Earth is typically 15 to 60 minutes, depending on the CME's speed. For a fast CME, now that warning window is 15 minutes. The large filament eruptions noted on the Sun today, July 26th, are being monitored for precisely this potential. The current NOAA 3-day forecast does not include a significant CME arrival. The forecast calls for quiet conditions through July 28th. But the filament eruption data coming in from NASA's SDO is being assessed right now by NOAA's forecast staff to determine whether any of the eruptions produced a detectable outgoing plasma cloud. If a stealth CME was launched, the updated arrival forecast will appear in NOAA's 1-day and 3-day forecasts as the coronagraph data is analyzed and the CME's trajectory is modeled. This is the operational reality of space weather monitoring at solar maximum. The quiet moments are not vacation days for the forecasters at NOAA's Space Weather Prediction Center in Boulder, Colorado. They are the moments when the subtle signals, the filament eruptions, the changing magnetic complexity of active regions approaching the limb, the minor fluctuations in the solar wind speed and density that can indicate an incoming CME before it is clearly visible in coronagraph images, require the most careful attention. Because the next major event does not announce itself. It appears. The historical record at solar maximum is instructive on exactly this point. The G5 storm of May 2024, the most intense geomagnetic storm in over 2 decades, the one that produced aurora visible from Florida, Mexico, and southern Europe, was preceded by an active period that had already produced elevated activity in the preceding weeks. The AR364 region that launched the May 2024 storm had already been the most active region on the disk for several days, before its most extreme eruptions. NOAA had elevated its flare probability to the highest levels. Forecasters were watching it closely. On May 8, 2024, active region 13664 produced an X1.0 class and multiple M-class flares and launched several CMEs toward Earth. On May 9th, it produced X225 and X1.12 class flares. On May 10th, an X3.98 class flare. On May 11th at 01:23 UTC, another X-class flare of magnitude 5.45.7 with another full halo CME. The KP index reached 9. It became the most intense storm since the 2003 Halloween solar storms. 5 separate major eruptions from the same active region in 4 days, each one a significant event in isolation. Together, they produced a G5 geomagnetic storm, the highest level on NOAA's scale, that reached KP9 and generated a DST index of negative 412 nanoteslas. For comparison, the 1989 Quebec blackout storm reached negative 589 NT. The Carrington event of 1859 is estimated to have reached somewhere around negative 1,750 NT. The May 2024 storm was powerful by modern standards and unprecedented in the era of most of today's space weather vulnerable infrastructure. And it was produced by an active region that forecasters had been watching, warning about, and issuing elevated probability statements for during the days before the sequence began. The lesson is not that G5 storms come without warning. They come with exactly as the active region's behavior allow, and at solar maximum that warning is often measured in hours, not days. This week's quiet window is the window during which the early warning happens, not for a storm that is already arriving, but for the conditions that will determine whether a storm of that character is coming in the next 2 to 4 weeks. The return of active region 4479 to the Earth-facing disk is the primary event to track. When it appears around the eastern limb, probably in the coming days, NOAA's solar region analysts will assess its magnetic classification within hours of its first appearance. If it is classified at a high complexity level, the categories used for the most flare-productive active regions, the machine gun sun scenario for August becomes credible. If it has decays, D, to a simpler configuration, that scenario becomes less likely from that specific source, though other developing active regions on the current disk could still produce significant events. The current solar disk, even in its quieter state, is not empty of interest. Several active regions are visible on the Earth-facing hemisphere in today's NASA SDO imagery, and the large filament eruptions flagged this morning represent unresolved uncertainty in the immediate forecast picture. The interplanetary magnetic field, the buzz component of the solar wind that determines whether incoming solar wind structures efficiently couple with Earth's magnetosphere, remains variable. KP3 is quiet. KP3, with a strong southward BZ spike embedded in a fast solar wind stream, becomes a G1 storm within hours. The distinction between those two outcomes is invisible in the current data and becomes clear only as the in situ measurements at DSCOVR resolve it in real time. The broader context for why this week matters beyond the immediate storm risk involves the trajectory of solar cycle 25 itself. Solar cycles do not have a sharp peak and an immediate decline. They have a maximum period, typically lasting 1 to 2 years, during which the high activity level is sustained with episodic intense bursts separated by quieter intervals. The July 2026 pattern, machine gun sun in early July, 3 CME sequence in late July, quiet window now, is consistent with being inside the maximum period sustained high activity phase. The question that August's activity level will help answer is whether this phase is continuing to build, has plateaued, or is beginning to transition toward the declining plateau that precedes solar minimum. Solar cycle prediction is not an exact science. The official prediction for solar cycle 25's maximum, issued by the NOAA NASA Solar Cycle 25 Prediction Panel, has been repeatedly revised upward as the cycle has exceeded the panel's initial projections. The panel initially forecast a relatively weak maximum, comparable to Solar Cycle 24, which was itself the weakest maximum in a century. Instead, Solar Cycle 25 has produced the most intense brief activity period, the May 2024 G5 storm of the modern monitoring era, more X-class flares in its rising phase than the equivalent period of Cycle 24, and a maximum activity level that has significantly exceeded the panel's original central estimate. This overperformance relative to official predictions creates a specific type of uncertainty for the current period. If the cycle has peaked and is now declining, the next several months should show a gradual reduction in the frequency of major active regions and X-class flares, even with episodic elevated activity continuing. If the cycle has not yet peaked, if July 2026's activity represents a mid-maximum burst rather than the maximum itself, then August and September could produce activity levels equal to or exceeding what July has delivered. The return of active region of 4479 this week is the most immediate observable data point for distinguishing between those scenarios. A strong, complex return from a previously productive active region, combined with the development of new active regions from the amplifying magnetic field of a still intensifying maximum, would suggest the latter. A weakened return from AR 4479, combined with a decline in new active region emergence from the solar interior, would suggest the former. 1 week of solar data does not conclusively answer a question that requires months of observation to resolve definitively, but it provides the most current, most real time update to the ongoing assessment of where this solar cycle is heading. What scientists are watching specifically in the coming days can be stated precisely. They are watching the eastern solar limb for the first appearance of active region 4479. They are watching the SDO and SUVI imagery for evidence of whether the large filament eruptions of July the 26th produced any detectable outgoing plasma clouds in the solar wind speed and density at Dioscoviar for early signatures of any incoming structures. Not yet resolved in coronagraph imagery. They are watching the emerging active regions currently forming on the solar disk to assess whether new magnetic flux from the solar interior is supporting continued high activity levels, or whether the flux emergence rate is declining, as it does in the post-maximum transition. And they are watching the BZ component, always the BZ component, the north-south orientation of the interplanetary magnetic field that determines, moment by moment, whether the solar wind arriving at Earth's magnetosphere passes over it and around it, or couples into it and drives the energy deposition that produces geomagnetic storms, induces currents in power grids, saturates transformer cores, drags down low Earth orbit satellites, and lights up the night sky with aurora. Every other measurement in space weather, flare class, CME speed, KP forecast, is preparation for that one number. Because when the BZ turns strongly, southward and stays there, every other measurement in the system stops mattering relative to the simple fact that the coupling has begun. The sun is quiet this week. The forecast is KP3. No GEO1 or greater storms are expected through July 28th. The sun at solar maximum is always quiet between its eruptions. That is not the same as saying the quieter it looks, the safer you are. Active region 4479 is on the far side right now, invisible. It is returning. The filaments that erupted this morning may or may not have launched a stealth CME that will appear in Dioscoviar's data in 2 or 3 days without significant coronagraph forewarning. And in the weeks after those questions are answered, the next active region after AR 4479 is already forming somewhere in the solar convection zone, its magnetic flux rising toward the surface, its eventual emergence as a visible sunspot a matter of time rather than if. This week's quiet is not the story being over. It is the story between the events that define solar maximum, the critical diagnostic window during which the system resets, the active regions cycle around, and the data accumulates that will determine whether August is another machine gun sun month or the beginning of the solar cycle's gradual return to quiet. 1 week, 1 returning active region, 1 unanswered filament eruption, and a monitoring system that updates every 3 hours every day, regardless of what the forecast says about how quiet things are supposed to be. Subscribe right now and turn on the notification bell. NOAA EA SWPC updates every 3 hours. Active region 4479 will appear on the eastern solar limb within days. And when it does, when NOAA issues its first post-rotation magnetic classification for the region that defined July 2026's solar story, this channel will cover it before it reaches anywhere else.